Getting big beginning of the semester.
Oh, yes. Okay, yeah, thank you for inviting me and letting me see the chaos in the first week of classes. Okay, so is that too loud or is that okay? Okay. So I'm going to talk today about this project we've been working on for several years now, but in the last few years we've really developed an understanding of this superconductor, and it's quite fascinating, so I'll tell you the story about it as we go along. Just should acknowledge support from various places, but in particular Gordon Betty Moore Foundation and DOE Early Career Award that funded a lot of the early work on this stuff, but also Air Force and state funding for the center as well. Okay, so there's two publications now that basically sum up the story here if you're interested in looking more closely once you forget everything I told you in the next 45 minutes or so. There's a theory paper actually that came out first, and then, because of the wonderful referee, community, this took a little longer to get out, the experimental paper. In any case, a lot of this work is attributed to my then postdoc, but now research scientist, Hyun-Soo Kim, and then theoretical collaboration with Daniel Achterberg and Philip Bryden. So here's the two publications. Okay, the greater team that does all the nitty-gritty stuff is here, or some of them are here at least. In particular, there's crystal grower Kaifeng Wang, and his wife is a DFT theorist. She also works with us and did some calculations. And Tristan is a grad student who will graduate soon, who runs dilution fridge and so on, does these things. And then in particular, I should thank the collaborations, in particular the collaboration with Ames Lab, Ruslan Prozorov's group, who was responsible for the penetration depth experiments that led to some key results that led us to our understanding. And then also Jeff Linnett doing neutron scattering at NIST, and Jonathan Denlinger doing photo emission work for the band structure. And then, of course, the theory colleagues. So Philip was a postdoc at Maryland at the time when we started this, and he's now in New Zealand. Okay, just to say a minute or so about our center, just so you can see some pretty pictures. The center essentially is the condensed matter experimental faculty group at the University of Maryland. It's about 12 faculty, and then many other affiliates in different departments and so on. We have a range of experimental apparatus for characterization and synthesis, all listed here. I won't go through details. And using these facilities, we can grow all kinds of different materials. And this is just sort of a nice, pretty snapshot of the types of materials we've studied: iron nictide superconductors, topological materials, heavy fermions, and so on, and all kinds of stuff, using different techniques. So if you're interested in this further, you can certainly ask me or talk to me later. Okay, one other thing I just want to advertise is this Fundamentals of Quantum Materials Winter School, which will be in January. We've had it 2 years now, and this will be the third year in January. It's a week-long school which has a list of seminar or lecture speakers in the mornings, and then the afternoons are filled with practical sessions where students of the school learn how to grow crystals, how to use different types of growth techniques, characterization, etc. So metal flux, arc melting, hydrothermal, thin film, X-ray, and so on, and actually get hands-on experience. It's become very popular, so we'll circulate some flyers when the time comes. You can apply if you're interested. Okay. So the Heusler family is a very large family of materials. This is one of the reasons we're interested in exploring it, because there's a lot of variation and phase space that you can explore. Just the crystal structure alone, so the Heusler is known as it comes in the Heusler and the half-Heusler phase, X2YZ and XYZ, where the half-Heusler is missing, obviously, half of the X positions. But the key difference is that if you see this cube here, half of those are missing, so that actually breaks inversion symmetry, and that's quite important for the understanding the nature of the pairing state in the end and other things. The other thing is that you can put in almost any kind of elements in this thing that spans the periodic table. Most of them are highlighted here, and that ends up giving you something like over 1,000 different types of compounds that are known. And that also leads to many different types of ground states. More recently, the topological properties that were highlighted, it's actually about 8 years ago now. So that means I'm getting older, right? Because this used to be a new slide. Not that I've been giving this talk for 8 years. No, that's not true. But there was a couple back-to-back predictive papers that were showing essentially the calculation of the electronic band inversion in this family of half-Heusler materials, or at least some subset of them, showing that depending on essentially the spin-orbit strength, you can show that some materials have a trivial band topology and some have an inverted band topology. And there's a nice example here where you just change scandium platinum antimony to scandium platinum bismuth. That actually tunes across this crossover line. And you go from this sort of trivial gap system to a inverted band gap system. And this has this topological twist, this magic non-trivial donut topology, if you want, that is potentially interesting. And this was shown by several groups in different, almost the same set of materials. They're all, I think, consistent, more or less. We initially wanted to focus on something near the crossing point and just try to be able to chemically tune through there and see if we can explore the transition between trivial and non-trivial topology. So we started in this area here, which is the palladium-bismuth compounds. This was some work about 3 years ago, got published. Just looking at the rare earth palladium-bismuth series, you can actually tune just by changing the rare earth position across this crossing point, theoretically, okay? But what was more interesting we found was that these materials are actually, of course, magnetic because these rare earths are, local moment magnetic elements, well-known F moments, but also superconducting. And we found that the TC, this is times 10, so the TC is about 1.5 Kelvin. And with magnetism, you can actually tune this down and then tune in magnetic order and even have a coexistence of the phases. So this is quite interesting, not only because it's essentially a new family, one of maybe 4 or 5 known magnetic superconductor families where you can do this. Borocarbides would be another example. But also because of the topology of the system. So, this is still an open question. At what point can you look at what happens to the predicted Z2 topology in this system in the presence of superconductivity and magnetism, or both? So this is an open question. Okay. Chronologically, this is the first material we studied, but I like to show it in this order because now we're looking at a platinum-bismuth series where it's a bit further off the line, and this then means that this has a very strong band inversion, should be a good topological insulator. So we started actually looking at yttrium platinum-bismuth. We essentially threw the dart at the dartboard and said, okay, let's start with that compound. And we did some crystal growth and basic stuff, and we found that it was a superconductor, which was surprising, actually, because it's a very non-metallic compound. It's essentially a semi-metal. The resistivity increases as you cool it down, and then below 1 Kelvin, there's a superconducting transition, which we found several years ago. This was Nick Butch. He was a postdoc at the time that did this work. TC is less than 1 Kelvin. HC2 is between 1 and 2 Tesla. The interesting things are that the carrier density is extremely low. It's in the order of 10 to the 17 or 10 to the 18 carriers per cubic centimeter. And at the time, that was actually the lowest carrier density, but then we got usurped by some strontium titanate work that came shortly after. But anyways, it's very low. It actually remains not understood how you can have such a low carrier density system and it become a superconductor. Yes?
Is that intrinsic or extrinsic?
Intrinsic what, semiconductor?
Well, it tends to have a part in a million sort of compared with 10 to 22 atoms for CC. So is that doped or is it?
It's, okay, well, I'll get to the band structure, but basically these guys are called so-called zero-gap semiconductors. So the neutrality point is right at this touching point. So whatever you want to call that. But in reality, in experiment, the chemical potential is typically a little bit down. So they're always hole doped. And that's so technically it's extrinsic, but we don't know the origin of this doping. And it's always the same. So we're not sure exactly why. Yeah. Okay. So there's a strong band inversion in the presence of superconductivity. That raises some questions about what's the nature of the superconductor. And then, of course, as I said, there's no inversion symmetry. So that also immediately raises implications for the pairing state in the system. I'll get into that a little more. So here's a schematic of this band structure, just to explain it a little more clearly. These bands the bands here are made up of the bismuth-based orbitals, the s and p orbitals. And what happens because of the strong spin-orbit coupling, you go from this trivial kind of topology to something like this, where the s-like band actually gets pushed down and the p-like band gets pushed up here, such that you end up with this gamma-8 band near the chemical potential. And the interesting thing really is, and this is what Philip and Daniel pointed out to us, is that because this crystal has such high symmetry, in other words, there's no other bands around, it's cubic, it's very high symmetry, and the chemical potential is very close to this touching point, you actually retain this degeneracy of the J equals 3/2 states of the P-like band, P-derived band of this gamma-8 band. And this immediately raised very interesting potential consequences for the pairing, because we know it's a superconductor experimentally. We know that this, at least the calculated band structure is quite interesting because you have this degenerate J equals 3/2 state. And then the question is, what is pairing? Okay, so the first step in some sense was to figure out if this indeed is the band structure. And that's the first part of data. And then the second question is to try to figure out or narrow down what kind of pairing states there might be by doing experiments on the superconducting state itself. So here's some photo emission data, and this is actually ongoing still, but this is some of the data that's in the paper, showing that the bulk band structure actually looks indeed very much like the calculated band structure. Now there's some band bending that we think we understand due to some surface potential, because these are photo emission studies done on these bismuth terminated states that should give some kind of potential shift at the surface that explains why it'd be different, but it matches down here, and then of course, if your eye is good, you see all these crossing points at 0, which would indicate some kind of states at the chemical potential, and we believe those are all I should say trivial surface states due to the bismuth termination. But that's part of the ongoing work. We know from quantum oscillations, which is a stricter measure of the Fermi surface, that these guys aren't around. So we think this is just an artifact of the photo emission study. I won't go into this, but this is just a photon energy dependence study showing that these bulk bands right here are indeed bulk derived bands. And so that matches the expected band structure. Here's a snapshot of the quantum oscillations work we did, just showing the Fourier transform of the data to make it simple. But it's pretty simple. There's essentially one frequency, or a nearly spherical Fermi surface, that's split due to the lack of inversion symmetry. So there's two spin split bands, or surfaces, I should say, shown right here, so blue and orange. One is spin up, one is spin down, if you want. And you can see that the splitting right here is of the order of 10 Tesla for a roughly 50 Tesla frequency. So it's quite large. So that's an indication of the strength of the spin-orbit coupling.
The oscillation in the transport, or?
This is transport, yeah. Yeah. And I'll show you a little bit of interesting data from more recent work where we've done some angular dependence of this, and there's some quite interesting effects due to the spin-orbit coupling.
What's FFT?
Fast Fourier transform amplitude.
No,
Oh, F of t, sorry. This is the frequency in Tesla. So it's, yeah, it's the Shubnikov to Haas frequency. Yeah. So 50 Tesla is quite small. So I should say that also matches the chemical, the carrier density measured, let's say, from Hall effect. So it's a very small frequency, which means a very small Fermi surface. Okay. Now this is unpublished work, but it's quite interesting. If you look at, and here's some raw data. If you look at the quantum oscillations in resistivity as a function of magnetic field, you can see the nice wiggles here. As you tune the angle, and this is basically going from like a principal axis 100 to 010, the equivalent axis. So sweeping through 110, for instance. This is a cubic system. You can see that at some point the oscillations completely disappear. And we were baffled by this for some time. You can see this, if you compile this data in a nice color plot, you can see this is the oscillation here versus field, and then you change the angle and you see that this thing just disappears at 45 degrees. You can do something fancier, which is, this is, sorry you can't see that, but if you point the field along 111 and then rotate about that, you can see a six-fold oscillation disappearance, which is consistent with the special angle being 110. We've worked this all out. We're now very good at drawing, you know, these funny angles and stuff, 3D pictures on our whiteboards. To figure this out, it's, you know, just shown the same way here. But basically, there's a special angle where the quantum oscillation amplitude disappears. And so we think we have a good understanding of this. First of all, this probably was explained to us by not Schoenberg, but Pepard, one of Pepard's old books, who explained that if you're in a limit of strong spin orbit coupling, in real space, these are atoms here, the black guys, in real space you'll have some splitting of the potential due to the ions in the lattice. And that will, in a certain configuration, give you a phase shift of the oscillation. So if you'll have two spin split, if you will, oscillations that will be out of phase by pi in this limit of strong spin orbit. And so this is what we think is happening here. And so I can show you, here's some data fit to some function that actually has two frequencies. So you remember there's two spin split Fermi surfaces. So there's, you know, one here and one here, it's almost identical. And they're just almost identical, so you get some beating effect, and you can actually see that here. Let's say you see this is growing and then it dies, right? It gets smaller and then grows again. And you can fit this for different angles as you tilt the magnetic field. So you can see, first of all, that the splitting actually goes away, and then at some point beyond 30 degrees, it disappears. The amplitude goes down. So what we think is that there's two frequencies that are nearly equal in frequency in orbit, but they're out of phase by pi. And as you rotate towards 45 degrees, they become exactly equal. And they're out of phase, so they destructively interfere. The other thing that we can pull out of this that's quite interesting is the actual phase shift. So there's a, if you want, there's a relative phase between the two frequencies, but there's also an absolute phase, and that's called the Berry's phase. So the Berry's phase is doing something quite interesting. It's going from, it's plotted in units of 2 pi here versus angle. It's going from 0 to 2 pi. So at some point, it actually goes through pi Berry's phase. It's quite strange. So that part we don't understand. There's some topology, there's some Berry's phase that changes as a function of angle. It's probably due to some spin orbit effect or texture on the surface. And then this is a simulation of this kind of two frequency model with pi phase difference between them, showing that, you know, you exactly reproduce the experimental data that we see in the measurement. So it's quite fascinating, and it's most likely, at least this part, is old physics. It's Pepard physics from years ago, but it's never been observed. So at least we don't know of an experiment with quantum oscillations measurements where the amplitude of the quantum oscillation suddenly disappears, you know, for all magnetic fields. That's not as far as I know, this has been seen. So it's a neat piece of physics that we pulled out of this experiment. Okay, that's, I won't go into this. This is more of the same data. Now back to the superconducting state. So this is this interesting normal state band structure we know has strong band inversion, strong spin orbit, and the chemical potential lies right in this gamma 8 band that's a J equals 3/2 degenerate band. J equals 3/2 in essence means you have electrons, or quasi-particles I should say, with spin half up and down and spin 3/2 up and down, right? Now, the question is, what happens when you pair these things? Now, it's been known, of course, for a long time that if you can, in principle, pair up fermions with high total angular momentum. And this is known from the days of thinking about these species of cold atoms with very high angular momentum, 5/2, even 7/2. So, for instance, if you have 7/2 quasi-particles, you can pair them into total angular momentum 7. That's it. I don't know what that's called, but that's it. Now, in the solid state, the question is, can you do this? And the answer is yes, if you have strong spin orbit, because then you have a total angular momentum J and M sub J being good quantum numbers. And that's why, we don't talk about electrons having spin 3/2, but these quasi-particles have J equals 3/2 character, spin character. So, this work that Daniel and Philip, they did this sort of whole calculation of all the possible pairing states given this band structure. And of course, as I alluded to, the interesting thing is that you go from the usual case where you have a singlet paired state of spin up and spin down 1/2, and the more rare spin triplet state where you have, let's say, spin half up and spin half up. But when you have higher spin species, you can go higher, of course. So you can go J equals 2 and J equals 3. Quintet and septet, I don't know what 7 is. Does anyone know what 7 is? There's probably no name for it, but J equals 7? No? Okay, that's your homework for the rest of the term. Okay, so then the question is, well, there's a big manifold of pairing states that are possible with this kind of structure of the band structure. And what's actually happening? Well, okay, before that, we should just, I'll pictorially show you what are the possibilities. So thanks to Philip, he put these nice slides together, which I would not know how to do with LaTeX, but he's a master. He has these states labeled pictorially with up and down, but also the skinny arrow is spin half and the fat arrow is spin 3/2. So now you can imagine putting these things together in different paired states. There's the usual spin half scenario where you have up and down, which is a singlet, or up and up, which is just one of the 3 triplet states. And of course, you know this elementary quantum mechanics, up, down, minus down, up, etc. The triplet is up, down, plus down, up, or, or down, down. But when you get to spin 3/2, of course, it gets more complicated, but it's the same story. But just as an example, even the singlet state is quite interesting because it's not just up, down, minus down, up, but it's a superposition of the spin half and the spin 3/2. And so on, right? So for instance, if you think about this, if you stare at this for 30 seconds, you'll get it, but it's, up, down, up, minus this part, right? So it's a singlet within a singlet, I guess. And then, of course, you can construct the triplet states in the same way, and quintet states and the septet states, and I just point to this one, up, up is easy. So spin 3/2 up and spin 3/2 up gives you total big J equals 3. Okay? Good? Of course, that's only half the story in a superconductor. You have the orbital part, so the total wave function has to be antisymmetric. So that gives you a very rich manifold of possible states. And okay, what is it? The simplest being sort of S-wave singlet. So you have an orbital part that's S-wave, and then you have a singlet that is this weird thing, but it's still just a singlet. That's the simplest superconductor you could have. The sort of next step would be something that's p-wave orbital, so it has a p-wave orbital part, and then something else. So you have to, of course, you have to keep the antisymmetric nature, so p-wave would have to have some odd parity part. Now that's complicated enough, but it gets even more complicated because if you remember, I said there's no inversion symmetry in this crystal, and that means that parity is not a good quantum number, and it means that the even and odd parity states mix. So it gets even more rich. But before I get to that, just to note that there's been other considerations of other materials in this context, and just as one example, this is nice work by Akita and company showing that in this famous heavy fermion superconductor, they think that there's even states up to J equals 5 halves, just shown by, I guess it's a color coding of the different pieces of Fermi surface in this system. And there could be some, mixing. I'm not sure exactly how this works when you mix these textures, but okay. So back to the question, you could have this very crazy high spin thing, but why not just have J equals 0 singlet is the simplest possible state. Usually, if you look up some classic textbooks on superconductors, they tell you that the lowest energy state is a S-wave singlet state, if it's phonons or whatever. Well, it's because of experiments. So the first experiment actually we did was point contact spectroscopy, which shows a very unusual shape to the spectra. I won't go into details, but basically this is analogous to some kind of tunneling experiment, but it's not exactly tunneling. And this is a sign of some very strange Andreev reflection process that's not typical of an S-wave superconductor. So that was the first indication of something weird, and we, of course, followed up with more experiments. The most important being the penetration depth experiment shown here, done by Hyun-Soo Kim when he was a student with Prozorov, and then he came to work with me after. The key to this experiment is that the penetration depth measured using a technique called tunnel diode oscillator is inversely proportional, square root proportional to the density of states. The carrier density. So if you remember, this system is extremely small carrier density. That makes it extremely hard to measure specific heat, thermal conductivity, etc. All the thermodynamic properties that scale with density of states, they're hard to measure, or they show nothing, basically, in terms of going through the superconducting transition. This doesn't. This is actually inversely proportional to it, so it's a very large signal. So here's the data. So yttrium platinum-bismuth is in black, and then just to compare to some other classic superconductors, this is a classic BCS S-wave fully gapped superconductor. In this range of fraction of TC temperature, this is just nothing. This is just an activated penetration depth that slowly rises as you go towards TC. In this classic D-wave superconductor, there's a nearly linear rise in the penetration depth. It's a signature of a nodal superconductor with nodes in the order parameter in K-space. In yttrium platinum-bismuth, we find that this is nearly linear as well. And then just note the scale. The scale here, which is absolute for this guy, is divided by 20 for this. So that just tells you exactly right there that the penetration depth scales with this inverse of carrier density very well. So it's a very nice big signal that we can measure very easily. So it's a perfect experiment for this system.
I guess it's not sure what kind of question, but what if you could visualize what happened with the order parameter, the function of position, and if you just applied a magnetic field to a good old-fashioned type 2, then you can get the flux oscillating penetrate. But here you're putting spins in it, but they screw up the order parameter in their own way. And do you get something like a spatial texture, or is there something going on that has that texture?
But you're talking about a vortex?
Well, no, I'm just saying
Lattice,
if you had a way to visualize the order parameter as function of position, is it just uniform?
In real space?
Yeah, in real space. Is it uniform? Is there holes in it? You talked about nodes.
No, it would be uniform, yeah. unless you have some kind of more exotic state like FFLO or something. And, well, if you have a what's called a finite momentum paired state, then you would have some real space structure that corresponds to that momentum vector inverted.
What
So-
does that mean, the other side of the try to translate back to
It's like if you have a small Fermi surface and a large one, and you pair between them.
Okay.
Yeah.
All right.
But we don't think that's what's happening here. At least there's no evidence for that. So this large penetration depth, of course, means that it's a large penetration depth, but the numbers are roughly on the order of microns. So that means that the penetration depth is of the order of the sample size, roughly speaking. That makes it also extremely hard to do things like NMR or study vortex physics, because the vortices are essentially huge, right? No, I'm saying on the order of, so the samples are on the order of millimeter. This is, it's macroscopic, that's all I'm saying. Yeah. Okay. And just to flash, also looking at other samples that with quote-unquote higher disorder, at least as measured by this technique, it shows nothing that goes beyond sort of quadratic behavior in the temperature, which is consistent with a superconductor that has intrinsic line nodes, where if you put more and more disorder, it doesn't destroy the nodes. They're not accidental. They remain, and then it just changes the temperature dependence a little bit from linear to quadratic. If it keeps going higher and higher, then that means you likely have some accidental nodes, and it's actually a fully gapped superconductor. So that's consistent with a true intrinsic nodal superconductor. So then if you take that experimental evidence and then use that to constrain the possible pairing states, the simplest pairing state that Daniel and Philip came up with is this particular state, which is called it's a mixed state because of the non-inversion symmetry, but it's a dominant septet state. So it's a p-wave septet state. Of course, it could be something different, but that would involve larger orbital angular momentum states like F wave and so on. And so just for energetic arguments, suggest that this is the more likely state. So it's a septet state, which means big J equals 3, and it's a p-wave orbital part. So in other words, that's the sort of simplest paired state that has line nodes. And they're actually shown here in the calculation. This is the spin up and down Fermi surface with the color showing the size of the superconducting gap, negative and positive, so it changes sign. But it actually changes sign on one of these surfaces here, and that's the black line. So that's a line node in the superconducting order parameter. So it's amazing. When they showed me this, I said, no, you just drew that, right? No, they got it from calculation. It's quite neat. Okay, there's other possibilities, so that's not the end of the story. It could be more exotic. So just for instance, Philip calculated the possible quintet states on this kind of Fermi surface for J equals 3/2. And this isn't even considering the mixed parity. This is just ignoring that to start with. And so this shows the texture of this order parameter in a quintet state. So first of all these states, which would be J equals 2. So it's like spin 3/2 plus spin 1/2 pair. These are all time reversal breaking, and they have this texture, which is a chiral texture. So for instance here, if you follow the phase of this order parameter, it winds around and gives you 2 pi around this node. And that would be topological in itself. So that would be a topological superconductor. And there's more exotic things, of course, too. And of course, it can be more exotic, too. But who knows what reality is? You have to just simply do more experiments, which are challenging. One other piece of evidence that we have from more recent work is looking at pair breaking effects, trying to help us understand the pairing state as well. So strontium ruthenate is a classic, I'll say quote unquote, P-wave superconductor because it's not concluded on, but it's likely, it's certainly a unconventional superconductor. It's known really well in this system that it's very sensitive to disorder. So all you need is 1 microohm centimeter samples, and you can't even see the TC anymore. But this is a classic pair breaking effect, Abrikosov-Gorkov pair breaking. And that only happens in a system where you have some sign change in the order parameter, such that if you start putting in dirt and you cause scattering between plus and minus, you actually destroy the state. What happens in yttrium platinum-bismuth? Well, this came out of a study where we were actually trying to dope the system, but it turns out it's not really doping it, but it's, at least experimentally, it's increasing the resistivity. So putting in gold into the system, we can actually go from this undoped behavior here up to, you know, almost 4 or 5 times the residual resistivity. Amazingly, when we do that, we actually have no change in TC that's we've measured so far. This is just transport experiments. This is unusual. You know, it's nothing like this behavior, of course. But we have to keep in mind that this scale here is meaningful, and it's not necessarily a large scale. This could be tiny compared to where you have to get to actually cause some pair breaking. The key parameter actually is the coherence length, which is extremely short in this system. It's 15 nanometers. And that's really one of the biggest puzzles about the superconductor. How do you have a 15 nanometer coherence length? It's very, very short.
Coherence length was measured by the
HC2, yeah. And I'm going to show you there's some complication to that as well that I'll show you in a second. So to study that and also to ask a further question, which is based on this really beautiful work on bismuth selenide by a few different groups, showing that there's actually some anisotropy in the superconducting state that arises that's breaking the crystal symmetry. And it's been called evidence of a so-called nematic superconducting state. So for instance, in bismuth selenide with strontium, you see this nice fourfold anisotropy here. Twofold anisotropy that breaks the hexagonal symmetry here. And so that's very interesting because it's nothing else is breaking that symmetry in the crystal. So we asked the same question, can we see something like this in yttrium platinum bismuth by looking at, for instance, HC2 as we rotate around? So we started to do this experiment. Here's a crystal, for example. We have a vector magnet, so we fire that up and start doing experiments. We found something very peculiar. So here's the first experiment, which is just a crystal where we rotate the magnetic field from parallel to current direction to perpendicular, but it's always in the plane of this crystal, like that. And you can see there's some wiggle here. This is the HC2, as determined by resistive transitions. You can see that there's some both twofold and a fourfold oscillation here. And we think, you know, perhaps the twofold could be coming from some displacement due to the current direction, and then the fourfold part is just the crystal symmetry. Good enough. That's not so bad. But what was more interesting was when we stayed transverse to current and just rotated from, let's say, you know, this principal axis to this one, which are identical, right? Crystal symmetry. And we see this very strong anisotropy. So this goes now from, this is this parallel to the plane direction to perpendicular, and it changes by almost, you know, 50%. And then there's some small other oscillation here. My student was doing this measurement literally on Valentine's Day, and he sent me this plot. So that's my joke. So yeah, we call it the Valentine symmetry. And anyways, this is just a cut through here, for instance, to show that there's some anisotropy. But you can see the anisotropy here. Yes?
Did you consider the inorganic fusion factors that may actually change the HC2 because of the crystal geometry?
Yeah, I'm going to show you next slide. So when you see this, you know, this is weird because this and this are identical directions. And we even did the experiment where we just literally took the crystal and rotated it and did the same experiment, and it follows the rotation. It's the same. Now, what was the weirdest thing was that we repeated this experiment, but on another crystal where the flat face was known to be 111, which is along the diagonal of the cube, and then rotating it into some unknown direction, basically non-high symmetry direction, which was just simply perpendicular to the current direction. So this is some facet, which could be 110 or something, but this direction is, we don't think is anything special. What we found is that it's actually the same. So it's the same kind of thing. And as I said, if we take this crystal and then rotate it, it follows the same orientation. So we think that it's actually a surface state. We think this is a so-called HC3 effect. That's another piece of homework. HC3 is a real thing. HC3 is just an enhancement of the superconducting state on a surface. So you can have an enhanced HC2. We don't understand these states. We're exploring them now. We're doing further experiments. But basically, I wouldn't say demagnetization factor, but it could actually be some surface state that's somehow enhancing the HC2. And we don't quite see it when we're perpendicular. But we're doing some experiments to actually test that, because it's a bit strange to me that, you know, if you have current voltage leads on a crystal that are on this side, it doesn't pick up anything that's on this side. You know, it should be something, but maybe not. So this is sort of 4 different samples that are kind of showing the same behavior, and it seems to be geometry dependent. So that another experiment to do next is to use some maybe square cross section, or maybe as close to cylindrical as we can, and then try to rotate and see if there's any change there. Okay, so the last question, I already alluded to this. The coherence length is extremely short. If you try to just put this in some kind of simple understanding, you can just flip that into an inter-electron distance, which is about 5 nanometers, just, you know, rough sketch. And this is how people talk about this so-called BCS to BEC crossover, this kind of length scale. Essentially the length scale between the paired states, the size of the Cooper pair gets smaller and smaller. At some point you cross over to where you have literally like molecules, like in a Bose-Einstein condensate. This is interestingly, you know, somewhere near this crossover. I wouldn't say it's crossed over already, but it's close enough that it makes life difficult in trying to understand what kind of superconductor this is. Another part that's very hard to understand is the Fermi temperature itself is on the order of room temperature, just based on the carrier density, essentially. That means that it's near the Debye temperature. And if you've done any course on superconductivity, at some point early on you go to what's called the Froelich approximation, which means that you take this limit where Fermi temperature is infinite compared to Debye temperature, and then you carry on in the calculation. If you can't do that, then you can't do BCS approximation. So that's already some theoretical limit. But the more fundamental thing, I think, is this thing, and just also considering these energy scales are the same. So there's people working on trying to understand this paired state. Where does it even come from? You know, let alone that it's some high spin exotic Cooper pair, but just what's the pairing mechanism itself? There's nothing around, really. There's no magnetism. It's likely a phonon mechanism, but it's not the usual phonon mechanism. Okay, so that's basically it. So I'll just summarize now. The Heusler family is quite rich. It's a large family. Even just the predicted topological materials are quite large in quantity. So we're exploring different types of those, and even looking how you can substitute this continuously and try to change the spin orbit strength, for instance. The superconducting state, as I've shown you, is quite exotic. First of all, because there's no inversion symmetry, so you have these Rashba split states. You have a mixed parity. The carrier density presents a challenge in understanding what's actually pairing it. You can mix in magnetism. I showed you just briefly for the palladium series. You can do that for platinum too. It's the same thing. So you can have coexistence of time reversal breaking magnetism, superconductivity, and the topological band structure. And then in this particular case, we studied extensively. We've shown evidence of these P-like J equals 3/2 states, taking that band structure together with the existence of line nodes from experiment leads us to this prediction that it's actually a spin septet, or dominant, I should say dominant septet state. The newest data is strange. We're still trying to understand this rotational symmetry breaking and whether that means that there's actually a superconducting state that's sort of lives on its own, independent of the bulk state. And then finally, what's the pairing mechanism itself? So thank you very much. Yeah.
So the topological, topological superconductors, one of the ultimate drives is to go to make very thin or rod-like systems to get from Bayron ways of making topological fusing. Do you have any angles that push in that direction or something?
Yeah, I wish I did. Well, the grand challenge is to find a so-called strong topological superconductor. And I wouldn't, at least my theory colleagues tell me that this would not be a candidate, at least I should say a superconductor that has nodes in the order parameter is likely not going to be a strong topological superconductor. So I'm not sure where to look for that kind of system. Other than what's typically done now, which is to think about a proximity effect induced state from a regular superconductor into some topological material and try to, and that's not even known for sure. Like in bismuth selenide, if proximity induced bismuth selenide, if that's a strong topological superconductor or not, or like what I showed, the strontium or copper doped bismuth selenide. So this is a good question. How do you do that?
So, Philip.
Yeah. The carrier density is quite low.
Yeah. Mm-hmm.
I wonder whether you can dope this crystal with something else and just try to tune this carrier density.
Yeah. So we. That was what we.
But gold is probably same balance as a platinum and doesn't change
Yeah. We were excited when we saw that. So, of course, we wanted to tune to the band touching point, and we were excited when we saw this. But when we did some Hall effect and even quantum oscillations, it didn't look like it changed. So we don't know why this is actually going up. It's maybe a disorder effect. I'm not sure exactly.
Well, what if you just change it rather than gold, use something else and change the balance values?
Yeah. So I have a student doing that, but it's tedious and takes a long time. I mean, yeah. So we're working on that. The one thing that's also interesting is when we put iridium, which is supposed to go the other way, it actually does become more metallic. So it's a bit challenging because these are nominal percentages and the actual percentages are much smaller. So we're not sure what's happening. Yeah. But that's one of the things we definitely want to do.
Have you actually looked at the vortices in this material? I think that since the penetration depth is so long, you probably want to use scanning split or something. So like, is that something you're pursuing? Because the shape of the vortices should tell you more about where the nodes are.
Right. So the best we've done was this work with Joe Strozio. So we're not doing that ourselves, but we tried some STM work a while back. I've probably showed you this. Now there's a complication here in that, so Joe did this millikelvin STM on surfaces, but the only cleave he could get was this cleave where there was some amorphous layer, which is probably some grain boundary. And he could anneal that with the tip and actually get some islands that were actually, what they show is that they're superconducting by proximity effect from underneath. So he would current anneal this part, and this would become a superconducting sort of nano island. And do spectroscopy and all that on that. And it kind of looks unconventional, but this is the proximity-induced state, so it's not clear what to say about that. But the vortices, oh shoot, I didn't show them. Okay. Well, in the paper, he shows that you can plant in vortices one by one in this island.
How can I'm surprised the penetration depth is a micron, 2 2 microns, you said. And
Yeah.
that's
Again, this is this
visible by
proximity-induced island, so I'm not
I
sure.
see. So he's saying maybe smaller. That's weird.
Yeah.
I would think penetration depth would be higher.
So the short answer is they didn't see anything unusual about the vortex structures, and even sort of the counting that you would expect something unusual if it was an odd parity superconductor. But it was always just limited by the fact that it's this island that's superconducting. It's not the intrinsic material.
So where are you going in this dartboard adventure now?
Oh, I don't know. I haven't taken the blindfold off yet. I'm just wandering around. Yeah, we're still working on this pair breaking, trying to understand that, and just doing substitutions to try to see how we can control this state. The palladium system is more interesting because TC can basically doubles. You can go to 1.5 Kelvin, and it's a little more accessible. But those crystals seem to be a little bit lower quality. So when you try to do penetration depth and so on, we see some weird features which aren't so clean. So we're still working on that. And right now we're actually looking at some of the magnetic species, like the mixed state systems, and finding that even the magnetism is quite unusual. So like holmium platinum-bismuth shows some unusual properties that we're trying to understand.
Well, let's thank JP again for a really intriguing puzzle.